we have started, we have given introduction of manufacturing, and then we started our first topic in, manufacturing process, that is metal casting. We discussed some rudiments yesterday, I mean some basics, and then we have solved some, 5, 6 or 7 problems, which are very easy. Of course, most of you have got the questions right. Okay, so let's continue from yesterday's class, and I'll warn you here, because metal casting is little bit of, is having theory in the sense like it's little theoretical rather than a problem solving thing. But yet after some time, when we are discussing about gating elements, okay, like design of sprue, design of in-gate elements, all these things, then we have some mathematics there, so then it will be very exciting. Okay, so let's wait for that, but anyways, we have to know all this stuff. There is no escaping from this. Okay, please be patient. Let's start. So continuing yesterday's class, we have different type of, we know what is pattern. Obviously it is replica of the original casting that we want to manufacture. So but it's not exact replica. What we do is that we to maintain the design, it means like we have designed some product, and then we want to maintain the same dimensions of the design product as you're manufacturing it, right? So to maintain the same dimensions of the design product, what we do is that we do some, or we add or subtract, some allowances onto the pattern, so that it will come which it is mostly equal to the design product. So we have seen 5 different shrinkage allowance, draft or taper allowance, machining allowance, right? And then shake or wrapping allowance, distortion or camber allowance. Now we will see different type of patterns. Not only different type of patterns in the sense like it is dependent upon pattern material, but here it is dependent pattern will depend upon the geometry and number of patterns we are using, all this. So let's discuss that. So this is a single piece pattern. So what is the use of single piece pattern? Why it is single piece? Because the whole casting is of single piece here. Okay, so let's say if the geometry is very simple, it's not complicated, and if you're not having any blinds there, so what happens, you can use it as a single pattern. So why single pattern here? Because this object, if you see, if you're having, this is the bottom one. Okay, let me take the, okay, so if you see this diagram here, what happens here, this is the molding flask. Okay, this is the molding flask. Fine. Now we have put this pattern like this, and then all around the pattern we have put the sand, and then we have rammed it. Fine, we have rammed it. After ramming it, now you have to remove the pattern. That is what we have to do, right? We have to remove the pattern, so that we are creating the cavity there, right? So once you are removing pattern, you have to retain the geometry of pattern itself in the mold in the molding sand. This is called molding sand. Okay, this is called molding sand. Let me write that. So this is, okay, what happened? Molding sand, and this is your pattern. Okay, now once you're removing it, you're not disturbing the sand. Your cavity is being intact. In the sense, your geometry is not getting disturbed. Whatever the pattern you have put inside, once you remove the pattern, the replica of same product will be getting, and you're not having any geometry disturbances. Okay, sir, I didn't get this, sir, single pattern. Let's see dual piece pattern, then we'll understand why single piece pattern is used. Okay, so let's go. So it is mainly used, you see, the important point here is it is of very simple shape and size. Very simple shape and size. Okay, fine. And it is also used for very small scale production, because how can you have very simple shapes in your original manufacturing process? You have complicated shapes, of course. Okay, fine. So now split pattern. Okay, so okay, let me take the diagram. Let me take this diagram in previous slide. What is happening? Yeah. So let's say if I have this kind of section, I section, like this. Okay. So if you have this section, I mean, of course it is like this. Okay, this is 3D, not 2D, something like this, something like this. Okay. A minute. Something like this, I section. Okay. So now, sorry, something like this. Okay. Okay. So now, if you want to put this, uh, okay, this is also easy to put. Let me take some other complicated thing. Okay, like this. If I section is something like this, something complicated like this, it's not very easy to remove. Okay. So now you can't directly put like this. So what you have to do, you have to split the pattern. If you're not splitting the pattern, what will happen is that if you see here, if you're putting it like this, and if you're completely putting this pattern like this itself, like let's say, let me draw the diagram for you guys. Okay, if it is like this, then you're putting in mud like this, let's say, and this is your, not mud, it is molding sand, don't call it as mud, molding sand, and you're putting molding sand like this. Now you want to remove this. If you want to remove this, there is a problem. What is the problem? The problem is this sand particles will be removed out, because obviously this is your material. When you're trying to pull this area, the sand particles will be coming off with the pattern itself. Now after removing the sand, I mean after removing the pattern, sorry, your mold, what you say, cavity will be like this. It will be like this, but it should be what? It should be what? It should be like this actually, right? But this section is removed here. So to avoid this kind of things, what you do is that you split the pattern like this, or you split the pattern like this. You're splitting the pattern like this, half. Okay. Once you split the pattern, half first pattern, second half of the pattern. You take these two pieces, and now as you are having two patterns, you have to have two boxes also. So you have top bottom box, this is the bottom box, and this is the top box. And bottom box is known as drag box, top box is known as cope box. Now you put one piece in drag box, ram it. Now you see bottom box is easy, right? If you have bottom box, you have this kind of, this thing pattern, half the pattern. Now this is very easy to remove. Your flat surface, like there is no problem. And like this, top box also you have. So top box also is like this. It is same thing like this. Same thing like this. Now you ram it. This also you ram it. Remove the pattern, and bring put the bottom box, and then on that you put the top box. The cavity is created like a dumbbell shape. Okay. And sir, how are we going to align them? So we have some dowel pins here. These are called dowel pins here. These are called dowel pins, and align them properly. And also you can also have some, wherever the partition is happening, that is known as parting line or surface. Okay. So in some cases, this is called split pattern. In some cases, you have to split into three. If you're splitting into three, then we have three different boxes. Obviously, if you're splitting into two, we have drag box and cope box. Bottom one is drag box, top one is cope box. This can be also a question, okay? Please do remember. And if you are dividing that into three pieces, then the top one is called cope box, bottom one is called drag box, as it is like two-piece pattern, but the between one is called cheek. The in between one is called cheek box. Okay. If you are splitting your pattern into three halves, three pieces, not three halves, three pieces. Okay, fine. So this is what is the split pattern. So that is the reason why instead of going for a single piece pattern, we are going for the split pattern. Okay. Next, loose piece pattern. Okay, fine, sir. We have done the split pattern. Now you see this is a very peculiar, what you say, casting piece. Now you want to remove this. So this is your pattern like this. See, Same thing. This is what I've drawn here. Okay. So this is all sand here. So when you're trying to remove this, what will happen? What will happen if you're trying to remove this? This section, this green color, this sand particles will come out, right? This will come out. This will come out sand when, because this is obstructing it. This is obstructing it. So what you'll do? So what we'll do is that, let me take this. Okay. So to make sure, because if you're pulling it, instead of getting the cavity like this, instead of getting the cavity like this, you'll get cavity like this, because you were supposed to have this thing like this, but this piece will this sand will come out. So that is the reason why what we'll do is that you make this geometry as loose piece and this geometry as loose piece. Okay, if you are making this A and B as loose pieces in the sense, those are not this is not a complete one pattern. It is having three parts: part 1, part 2 and part 3, and 2 and 3 are loose pieces. Now what we'll do, you put it, you ram it, and happily you can remove this. But these loose pieces are stuck inside this thing. Okay, and slowly, obviously, if you see that, if you are doing that, actually when they are removing it, assembling it, you have some kind of a thread. Actually, there is some kind of a thread like this. So slowly, by pulling this thread very carefully, skill is very important here. Very carefully, you can remove that loose pieces. You can remove these loose pieces by using this thread without disturbing the geometry here. This is very complicated geometry, right? It means the sharp edges are there to avoid that sand to be intact. So what you do, you remove these loose pieces with the form of some kind of threads or some kind of small steel bars, small steel bars. So now you have retained your shape. Happily, you have retained your shape, and that is why, as we are making these two things into loose pieces, this is called loose piece pattern. Okay, so what we have discussed: single piece pattern, split pattern. In split, we have discussed about two splits and 3 splits also, and then loose piece pattern. Okay, what if we remove the pattern sideways? Sideways in the sense like what you say, like this? I mean, right side, left side. What do you want to say, Pravi? What was your question? Sideways in the sense like if these are loose pieces. So sorry, these are not loose pieces. 1 minute. So these are loose pieces like this. So you want me to remove what, like this? That is what you're saying. Am I right, Praveen? Like if you remove the pattern facing you, my side, like this. How can you remove? So this is cross section. Okay, this is cross section. This is a cross section. This is a full cross section. Okay, this is like this, and this is a simple cross section. This full in box. You can't remove towards me. You can't remove that. You can't remove towards me. Obviously, you have to move this side little bit and then pull up. Move this side little bit and then pull up. Okay, you're understanding? Yeah, this is a cross-sectional view. Please do remember, this is a cross-sectional view. So what is that? Your molding box is like this. Okay, now I got your point. Your molding box is like this. Some cross-sectional view we are taking it. Some cross-sectional view we are taking it. That cross-section is this. Okay, cross-sectional view. It's not a front face or whatever it is. This is front view. Okay, cross-sectional view. Okay, you have to, if you are having loose pieces are like this, you have to first pull this side, then go up, and pull this side and then go up, like this. You have to pull like that. Okay, okay, fine. So this is what is loose piece pattern. Next, match plate pattern. So we have seen here, we are aligning it with dowel pins. Okay, we are aligning with dowel pins, but how sure you are that these two, top one and top pattern and bottom pattern are aligning? So it might be like this also. We don't know, right? We don't know. Can be happen like this also. Can be happening like this also. There is no proper alignment. Okay, the top one and bottom one are not aligned properly. So to make sure that those are aligning properly, you have a plate, and that plate will match the top and bottom. So that is what is the match plate pattern. You are using a plate in between instead of directly placing on top and bottom. You are using some kind of a plate to match the top box and bottom box, so that your cavity is exactly the geometry that you wanted to have. Okay, so it's to eliminate the mismatch of cope and drag cavities. That is why you are using this match plate in between. This diagram is very self-explanatory here. It's very clear here, right? You can easily see the top one and the bottom one are matched with the help of this plate, and this plate is known as match plate. Okay, so that is what is your match plate. So again, I'm repeating, we have discussed single piece pattern, split piece pattern, or loose piece pattern, match plate pattern. Okay, next, cope and drag box pattern. Okay, fine. So here what we did, we are okay, fine. So okay, in this diagram, let's say in this diagram we have put it. Then how are you pouring? You have completely clamped it, no? How do you want to pour the liquid? Where do you want to pour the liquid? So what you do, you add some kind of sprue here, like this. You have some sprue, and from the sprue you will add. Then it will happily pass on to all these things, and then to accommodate the liquid and solidification shrinkages, you have to put some kind of riser. This is called riser. Okay, and there are some gating. These are called gating elements. This is sprue and riser. So if these are all extra, when you are ramming it, you have to put separately sprue, you have to put riser, that are also made up of wood only. You have to hold them properly, and then you have to ram it properly. Okay, if you have seen casting, you will be appreciating this. Okay, so sometimes what will happen, I don't want to add this sprue riser separately. I will combine that riser gating elements all into one place onto top and bottom pattern. So riser also is accommodated into the pattern. Generally, riser is separate from the pattern. You are putting riser separately and pattern separately. But if you are putting riser element also into the pattern, you are putting the geometry of riser into the pattern itself, and that is called cope and drag pattern. Okay, so see, in cope box you have riser pattern here. This is what is your cope pattern, and this is what is your right. And these are all gating elements. Actually, this is your object. So I'll underline this. So this is your actual object. Actually, this is your actual one. Okay, and this one. So this is your riser, this is your in gate, all these things are there. Okay, so please remember, in cope and drag box patterns, what is there, we are trying to incorporate the riser and gating elements into the pattern itself. That is why it is called cope and drag patterns. Okay, 1 minute guys, 1 minute. Okay, give me 1 minute, guys. I have to go pick up one delivery. 1 minute, just 1 minute. Okay guys, I'm back. Okay, so that is scope and drag pattern. Next, sweep pattern. Okay, and now you have to understand here that sweep pattern is not replica of, generally what was the pattern definition? Pattern definition was the replica of the original object or original casting. But sweep pattern is not a replica of original casting. It's a 2D element. Okay, so if you, let's say here, if you see on the left hand side, if you see, you want to make this kind of a pot. Okay, you want to make a this kind of a pot or this kind of a solid object. So your pattern is not exactly this is, same pattern. There is no need to make this pattern. You can make a single, what you say, 2D shape here. This is your 2D shape. This is your 2D shape like this. Now, I mean, of course, this is having some thickness here. If you have some thickness, now what you do, you dig a pig. There is a pit here. It's a very big pit. It's not in molding box. We are not doing this thing in molding box. We are doing this thing in a very big pit. Pit in the sense like it's a big hole where you put the sand. And please do remember, green sand doesn't mean that sand is in green color. Green sand means sand plus some moisture. Sand plus some moisture, and that is why it's called green. So if somebody is saying it is a green, means the sand is consisting of good amount of moisture. Okay, it's wet in nature. Wet in the sense it's not fully wet. Some kind of moisture is added into that. Some kind of water is added to it. Because of that, the sand is in moisture wet state, and that is known as green sand. Okay, so you add some green sand into the pit. Okay, and then you dig it and it like this, and you have some axis of symmetry like this. Then you revolve it like this. You revolve it like this. Once you revolve, if you see, you get this kind of cross section like this. And then obviously when you're revolving it, you have good, this is top view. You have some kind of nice, molding cavity that is being formed, and then into this cavity you pour the liquid metal and then solidify it. Hope you, I'm making your this point clear. Okay, it's a 2D piece, and you are using the axis of symmetry, and with the axis of symmetry, you're trying to revolve this and sweeping it. You're sweeping the sand there, and that's why this pattern is known as sweep pattern. Okay, this pattern is known as sweep pattern. Okay, fine. Next, okay, let me write. This is green sand is sand plus moisture. Okay, won't the post affect the casting well? No, you remove the post. It won't affect. Actually, what this here, they are making it like this, but you remove the post itself. You remove the post. It will be, it will, I mean, this post is very thin here. They have what you say, they are making it more exaggerated. It is very thin, and they can disjoint it. It's not completely, it won't be there when you're pouring it. Good question. It won't be there when you're pouring it. Yeah, good question. Good, very good. Come on, guys, let's proceed. So now here we are discussing about the follow board pattern. So follow board pattern, these are all very miscellaneous patterns, but anyways, let's discuss that. So you see, this is your object that you want to manufacture, and this is what is your pattern. Okay, pattern. This is your pattern. Now, if you are trying to ram it, if you're trying to ram it, this is having very small thickness. See, the thickness is very small. When you're ramming, it might happen. It might only. It's not sure that it's going to happen. It might happen that this will get damaged here. This will get damaged here. So what you have to do, you need to have some support for it, and that support comes in the form of follow board here. So this is called follow board. So see, this is your follow board, and you are adding some material, and then you remove this. Okay, and that is called follow board. So if you read here, a follow board is a wooden board, and is used for supporting a pattern which is very thin and fragile, and which may give way and collapse under pressure when sand above the pattern is being ran. So that is the reason why we are using follow board pattern. And I also didn't see this till now. So all these patterns I have seen. I've seen all these patterns, but I don't know. I've been to so many manufacturing units. Till now I didn't see this pattern, but hopefully somebody is using it. Okay, fine. Next, and I've seen this pattern. It's a very important pattern, skeleton pattern. Let's say you want to make this frame. Sir, it's difficult to make this in casting. No, it's easy. How? First you have to make this pattern like this. This is your wood only. So what you do, you take a base, on that you take this kind of wood. You're placing your wood like this, and this is what you're putting it like this. Okay. Now what you'll do, you put sand into this. You are putting sand because there is a space here. This is all space, right? You're putting sand, and then the extra sand, whatever is there, you are having a trickle board, and the extra sand what is there, you're just sweeping like this, and the sand is taking exactly this shape. The sand is taking exactly this shape. Okay. Now what you'll do, you remove this wood, slowly remove this wood, and remove this. Now once you remove this, obviously you have some kind of path like this. You have some path, right? You have some path onto like this, right? You have some path, and this is your path. And then you pour liquid metal. Once you are pouring liquid metal, what will happen? It will take this path. Happily it is filling. If we have seen, I don't know how many of you have seen a Game of Thrones TV series. If you have seen in season, I don't know which season also. If you see, they used to pour liquid metal into some kind of a small channels, like it will be like this, small channels, small channels like this, and uh, like this. They have good knife they used to have. So they used to pour, and the channels they used to make knife swords for fighting. If you see, I don't remember, but anyways, if I have time, I will clip. I mean, I'll take the clip out of it and I'll show it to you maybe in the next week or somewhere. I don't remember which season it is, so I have to find it out. And that is what is skeleton pattern actually. That is what is exactly skeleton pattern. They have used skeleton pattern to create that kind of a mold cavity, and in that mold cavity they are pouring some liquid metal, and then they are getting the sword. Okay, so they are getting sword out of it. Okay, fine. So this is what is called skeleton pattern. Okay, fine. So that's the end of metal patterns, different type of patterns. So let's solve some 3-4 questions on this skeleton, all these different type of patterns. Okay, and yesterday I promised you that I'll be putting some questions in the PPT itself, but as I mean, yesterday it got late, we 10:30, 10:45, so morning also I couldn't wake up early, so because of that I couldn't put the questions in PPT. For today, for only today, we'll solve like yesterday only. From tomorrow itself, or maybe day after tomorrow, what we'll do is that I will take each question and I'll put into the PPT, and then we'll solve in PPT itself. Okay, please I okay. So yesterday we have solved. Thank you. Thank you for understanding. So yesterday we have solved till 7th question. Hope will you can solve some questions. Okay, what is the answer for 8th question? Anyone? Oh, this shell molding. Okay, forget about this question. What is ninth one? Tell me. Ninth one. Anyone with the answer for ninth one? Okay, ninth one. Everybody is. I want answer from everybody, please. Even though it is right or wrong, doesn't matter. Nobody is going to judge you. Okay. Okay. Somebody is saying A and somebody is D. Oh, okay. Okay. Guna, I feel you have to check your answer. In loose piece pattern, did we even see a parting line? In loose piece pattern, did we see any parting line? Please go to loose piece pattern. Are we having any parting line here? We don't have any parting line, right? We don't have any parting line. Okay. So answer is A. You're right. See the options. Making, okay, let's not see A. So let's go from bottom to top. Integrate casting split at parting line. What is this? Which pattern? Which pattern will use this for this? What is the pattern that we are going to use for this? Anyone? Which pattern we are going to use for this? For this kind of things? Anyone? We are having some integrate shapes. Which kind of patterns we are going to use? Is it not split pattern? Is it not split pattern that we are going to use this? So this is split pattern. Yes, very good, very good, very good, very good, everyone, very good, very good. Large scale continuous production in machine moldings. Okay, so this continuous production we are not using for loose. Yes, gated. Amazing, amazing, Satish, very good. And large and axisymmetrical castings. What is this? For axisymmetrical, what is the pattern we are going to use? For axisymmetrical, excellent, excellent, excellent. Again, sweep pattern. So obviously, loose piece pattern we are going to use for making integrate shapes where removal of some portions of pattern are not possible. Excellent. Answer is A. What about next one? What about next one? Let's try to think. I didn't discuss this, but anyways, try to tell me some answer. Okay, no problem. Try to guess it. Try to guess it because see, sometimes this is not. I can't give you some 10,000 to 20,000 questions and practice them. Out of them only questions will come. Question paper can be of anything. The question paper who is setting the person who is setting the HL paper, he might not refer any books. He'll directly give with his experience. So if you are seeing some new questions, you should be able to guess it. How you are going to guess also is very important. So please tell me answer for 10th one. Please tell me answer for 10th one. We'll discuss 11th and 12th. Good that you are ahead. Deepak, very good. You are ahead, but please tell me answer for 10th one. And even though if you're not knowing the answer, guess it and tell me why. It's very important. So shrinkage we have seen. So something double shrinkage is talking about. So what is this double shrinkage? Okay, answer is D. Prabhakar is saying D. Any reason, Prabhakar? Any small reason in one line reason? Okay, Naveen is saying C. Deepak is saying A. Okay. So I need answers. I need why. At least can you tell me in one line why you are saying like that? Okay. So okay, fine. Okay, fine. So the answer for answer for 10th one is D. D. Why it is D? Why it is D? I'll tell you. Here, single piece pattern. Okay. Okay, sir, you are making pattern. From where you are making pattern? For making pattern also you have to have a pattern, right? Am I right? Am I making my logic here clearly? Okay. You are making pattern. Pattern you are making, and from pattern you are making casting. It's okay. But for making pattern, you need to have some other pattern, right? So now that will be your master pattern. That will be your master pattern. Okay, that will be your master pattern. Now for master pattern, the problem is it will be two shrinkages. Shrinkage number one is the uh, allowances that you are trying to put for the casting object. Let's say if you are taking aluminium, so then you consider shrinkage allowances, metal allowances. So all the shrinkage of actual metal, the shrinkage of the actual metal is one shrinkage, and pattern material also will be shrinked. No, because let's say your master pattern is some you know I don't know, I mean some steel object, and then you are putting wood. So wood also will be, you're making pattern now. You're making pattern. So wood also might increase and decrease. So for wood also you have to consider, right? So for wood also you have to consider. So one shrinkage in double shrinkage, one shrinkage you are considering in the respect of metal. One shrinkage you are considering with respect to metal. Another shrinkage you're considering with respect to pattern itself. For wood also there might be, increasing and decreasing of, increasing of volume or decreasing of, because I already told you. See, I went to some pattern shop. They're maintaining proper humidity. They're maintaining some kind of temperatures, so that they are trying to reduce the problems with wood, because if you are pouring some water into the wood, they're pouring some water into the wood, the wood will be expanding or compressing it based on the temperature and humidity. So in double shrinkage is applicable for master pattern, and this master pattern is used for taking pattern itself. In the master pattern, will make the shrinkage allowances of metal that you're trying to pour, and also the pattern that you're trying to make. Am I making myself clear? Is it okay, guys? Answer is D. Okay. Yes. Fine. What about next one? What about next one? What about next one? Okay. 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 Yes. Excellent. It's a simple question. Obviously wood is not disposable. Disposable in the sense, what I'm saying is that this polystyrene patterns, you directly, these are very light density. These are all plastics basic. Then you can pour some directly liquid metal can be poured onto the pattern itself. Then it will be disposed. You can't even see that. It will evaporate. Okay. Answer is B. Okay. Core prints. Okay. We didn't discuss this. We'll discuss this. Okay. We'll stop here and let's go back to the slides. Very good. Okay. Fine. So, chalo. Let's go to the next slide. Okay. Now, core. I told you already what is core. Core is nothing but you want to make some hollow section in your casting. Okay. If you want to make hollow section in the casting, obviously you have to put something in between in the liquid metal. What I'm saying is that if you want to make, let's say if you want to make this kind of an object, and this is the hollow section here, this is the hollow section, this is the hollow section here, this is the hollow section here. Now what you do, you make the hole like this, you make the hole like this, and then if you are pouring liquid, there won't be any hollow section created. So what you do, you put some other sand particles in between like this. This is your sand particles. This is sand particle made some kind of a rod kind of thing. This is sand. Okay. Now pour it. So wherever it is empty, the liquid metal will be taking its place like this. It will take here. Actually, it will take around this thing. Once it got solidified, you remove this. Then hollow section is formed. Okay. Now, okay, sir, I'll put some core material inside this thing so that I'll be getting hollow sections. But where do you want to place the cores? Where do you want to place the cores? That's very important. I can't place it somewhere here, no. I want to place exactly where I want to have. I want to have, let's say, I want to have exactly at center. So now you can't directly, you can't put the core like this. Okay, sir, I'll put core like this. Okay, let me draw it again. Okay, sir, I'll put the core like this. I'll show you that 1 minute. Okay. So let me take another figure, another this thing. So okay, sir, I'll put core like this. But after pouring liquid metal, this is having some density, core material is having some density. Liquid metal you're pouring and liquid metal is having some density. Due to density differences, this core might float up or this core might come down. We don't know. It can't be exactly hanging in between, right? So to make sure that this core is at exactly same place, you have some protrusion. You have some protrusion like this. This is sand, okay? This is all sand. This is all. Some kind of protrusion is there. Okay, let me draw the protrusion with some other color. This kind of protrusion is there. Okay. So this kind of protrusion, extension to that, and which is stuck in the sand. It is stuck in the sand. Now, even though you're pouring liquid metal, it can't go up and down. Why? This is obstructing it. This part is obstructing it. its movement, the core's movement. So, and these protrusions are called core prints to identify where we have to place our core. Okay, so that is very important. So you see, these are all core prints. This is core print. This is also core print. See, this is your core print here. Core print. Okay, and this is exactly your core. Okay, and also sometimes you wanted to have some not complete hole, you want to have some blind hole. You know the blind hole, right? Blind hole in the sense it is not complete hole. It is not complete hole. It is not like this completely. You have some blind hole. Okay, if you have some blind hole, you can have core print. This is core print. It's okay, fine. But to make sure that the between portion is not hanging, or it is not bending, you have these things called chaplets. They are called chaplets, and those will support your core as well. Those will support your core. And chaplets are also used for directional solidification, but we'll not discuss that. Okay, since the core is completely blocks the drag box cavity, how the molten metal is filled there? You don't want to fill there. You want to block it, Naveen. You want to really block that molten metal not to fill there, right? No, then only then the hole is being formed. You don't want to fill there, no? Am I right? So let's say if you want to make this, yeah, you got the point, right? You don't want to fill it there. That's the reason you want to block it. The main purpose itself is for blocking. You don't want the metal fill there, then only the hole is being formed. Yes, good, good. So now, so these chaplets are very important. So when you are having some blind holes, so chaplets are placed, and these chaplets are made up of material, material which is same as molten metal. Let's say this is aluminium. Metal that you're trying to pour is aluminium, and this also is aluminium. Your chaplets are also made up of same material, so that it will directly completely fuse inside the metal, molten metal, but initially it will try to support the core not to bend here and there. The hole should be exactly straight. It should not be something bent like this, right? That is what the core. Okay, core and this. Now, okay. So now something is happening. What is happening here? I told you already. This core is having some weight. This weight of core. And obviously, when you are pouring liquid metal here into this, liquid metal will try to have put some buoyancy force. Some buoyancy force is acting onto core, because this is liquid. Obviously, if you're jumping into water, one thing you're going into the water because of your weight, and you'll some kind of buoyancy force is acting onto your body, so that you'll try to float, right? So if these two are balanced, it will be there itself. If these two are not balanced, if weight is more, it will come down, or if weight is less and buoyancy is more, it will go up. But in this case, it will not go because you're obstructing it. But you're obstructing it, but this also can take some. This is not some material. This is sand, no. This is sand, no. So the core prints will be taking some force because of the difference of buoyancy and the weight of the core. Now we have to design that. So what is the force and all that, we have to discuss that. Okay, let's go to the next slide. So this is the net force that is acting onto the core. Weight of the core minus buoyancy force minus weight. Buoyancy force is in top direction and weight will be in the bottom direction. Okay, so that is what is the net force. Okay, so then buoyancy, if you are saying what you say buoyancy, what is buoyancy force? Buoyancy force is nothing but weight of the liquid metal displaced, right? And minus weight of the core is weight of the core. This is buoyancy force, and this is the weight. And weight of the liquid metal displaced is what? We can write weight. What is weight? Weight is m into g. And what is m? M is density into volume into gravity, right? And now here we see, if you see this thing, rho gv is weight, density of liquid metal into gravity into volume of core, because when you are trying to put the core inside, that same volume will be displaced, right? So volume of the core itself, and weight of the core is this, that is density of core into gravity into volume of the core. You can take G into Vc common and density of metal minus density of core. Okay, that is what is your, what you say, the net force. Very important formula, very important formula. Okay, but I hope they won't be asking this kind of very important formula. Very important. Okay, so they won't be asking exactly to solve this question. Sometimes it might happen that they'll be giving you easy, numericals. Like what I say is that they might be saying that, okay, the gravity, let's say gravity is 10, volume is 10 cube, density is 20 minus 10, something like that. This calculation is easy, so they might ask, but the calculation wise it won't be that difficult. Okay, very important formula. Please do remember this. Okay, this kind of formulas you have to write in your short notes. See, I'm telling you right now, the important thing here is that you should be able to put some short notes so that you will be able to write all the formulas one by one in book, chapter wise in the sense topic wise. For casting, one place; for welding, one. Or you keep three books. One book is for thermal and fluids, another book is for design, that is your strength of materials, machine design, whatnot, and then another book is for section 4, another book is for other things, math, whatever it is, aptitude, whatever it is. Keep four small books, or maybe take a very big book and make it into four parts, and in each part you write all these things, formulas. At the end of your preparation, you can easily revise it. No need to go to another, go where it's okay, here it is the formula, in which slide it is there. All these things will be difficult. Make a habit of making short notes. Okay, that is my tip here. Okay, fine. Next, so already we have discussed what are core prints. So core prints are projections on the pattern and recess in the cavity to position the core properly. Okay, chaplets. What are chaplets? I already told you them. These are metallic objects used to support core inside the cavity. Already we have seen it is supporting the core, right? And then these are made up of same material, as I told you already, same material as casting, and become integral part of it. After pouring the liquid metal, it will vanish. It will completely fuse inside the liquid metal, and then it will be integral part of casting. Okay? So those are the uses of core prints and chaplets. Okay. Now, so let's see this question. So a hollow casting is produced using a cylindrical core of 100 mm diameter. What is given? Core of diameter is equal to 100 mm. Okay, and height of core is again 100 mm. So what is the volume of core? Volume of the core is cylinder, right? Pi by 4 d square h, right? So then you do some calculation, pi by 4 into 100, or you can say 0.1, because this is mm, 1 square into 0.1, you get some value. So you got volume of the core. Now density of liquid metal. What is the density? Density is equal to liquid metal, that is density of liquid metal, rho m, is 2600 kg per meter cube. Okay, and density of core is 1600 kg per meter cube, right? What is the net force? What is the formula of net force? Force net is equal to, we have seen already formula. What was the formula? G into Vc, gravity into volume of the core into density of liquid metal minus density of core. Okay, so gravity into volume of core into rho m minus rho c. So what is F net? F net is equal to, gravity is, let's say, 9.81 into volume is Vc, we calculate it from here. Okay, this is what is your volume of core into, what is the volume of density of liquid metal is 2600 minus 1600. Then you get some answer in newtons. That is what is your solution for the question. Okay, so let's see the solution. This is the solution. Okay, this is the solution. Hope you got the point. Very easy. This kind of questions will be asked, can be asked. Okay, fine. Next, so molding sand is made up of some ingredients. some kind of a recipe, right? You have to have some add something. It's not only silica, it's not only sand. Sand is 70, 70 to 80%. Let me take another this thing. Okay. Clay is for binding the material, powdered form. It might be bentonite, kaolinite, whatever it is. Then add little bit of water. That is making the sand green sand, moistured sand. Then small additives. Why these additives? This will be acting as some kind of a binders, or it might be improving the properties of molding sand. So there are some properties of molding sand. We'll be discussing that in the coming slides. Okay. So these additives are added to improve the properties of sand. Okay, fine, good. So what are the properties? The properties are this. Okay, first is refractoriness. Obviously, you have to withstand, because your pouring temperature is around 1700 degrees centigrade. You're pouring. If you're pouring on anything, it will burn. It will burn, or it will be damaged. But your molding sand should be taking or withstanding, or it should be capable of taking that much of temperature, and that ability is known as refractoriness. The ability to withstand the high temperatures of liquid metal. And it should not fuse. Silica should not fuse. It should not mingle, and it should not mix up into the molten metal. Okay, that is what is called refractoriness. Okay, next, permeability. Okay, when I'm having some kind of molding cavity like this, and this is all sand, and when I'm pouring liquid metal into this, now there is some reaction between the molten metal and the molding sand, and when you're pouring, some atmospheric gases also will be mixed into this. All these gases should be escaped out. It should be escaped out. It should not get trapped inside. If it is getting trapped inside, some kind of defective castings will be formed. All the air bubbles will be there inside the casting. Some air bubbles will be there. All the air bubbles should be gone out. They should go out. Right? That kind of ability to allow the gases to escape from the molding sand is known as permeability. See, the ability of molding sand to allow the gases to escape is known as permeability. It is expressed by permeability number, obviously. Okay, let me take one thing. Okay, so if we have some box, or okay, this is full of molding sand. Okay, this is full of molding. You made kind of a molding sand in the form of a cube. Okay, this is a full molding sand. There's no cavity, nothing is there. Okay, now you seal the top, you seal the bottom, you seal the front face also, you seal the back face also, and this face is there, and this face is allowed. So from this face you allow some air. Okay, and this air is coming out. This is outlet and this is inlet. Let's say, if at all I'm trying to pass some 100 or 1000 centimeter cube of air, volume of air, and it is taking, let's say it's taking some 10 minutes. This is sample 1, and another is taking time, sample 2 is taking 5 minutes. This is 10 minutes. Okay, so it means that second one is allowing the air very fast, right? It means that the second one is more permeable, because your air is coming out very fast. It is not taking much time. Happily it is coming, it is allowing it. Okay, and the first case it's not allowing it, because of it might be happening that the sand particles are very nearby, and the air which is traveling from this side to this side, what is happening, it might be having some so much of intricacies and tortuosities, all these things will be there. Okay, because of that the air is passing little slowly. So obviously if you see, this is more permeable, this is less permeable. So more permeable in the sense, permeability is inversely proportional to time. More time, less permeable. Less time, more permeable. Okay, so that is the reason why I have written here permeability is inversely proportional to time. Okay, and the formula is very important here. You have to know it. This one, that is Pn is equal to V into H by PAT. Permeability number is equal to volume of the specimen, volume of not molten metal. This is for sand only. From where the air has to be escaping, the air should be escaping from the molding sand, right? So this is the volume of the air that is being passed, volume of the air that you are trying to pass. Okay, let me take pen. Okay, volume of the air that you are trying to pass. Height is the specimen height. Okay, and P is the pressure difference. Obviously, if you want to pass air, obviously you have to create some pressure difference. Let's say this is P2 and this is P1. Obviously, P1 should be greater than P2, right? Then only it will move. Air will move from left to right. Okay, so and A is the area of cross section of the specimen, which is cylindrical in shape, standard specimen, and T is the time. This T is the time through which it is being passed. So it is inversely proportional. So you can use this formula to calculate the permeability number. Okay. So volume of the air, standard air passed is 2000 centimeter cube. Standard specimen height of the sand that you're trying to test is 5.08 centimeter, and the cross section is circular, that is pi by 4 d square, and d is also 5.08 centimeter, and this is fixed, this is fixed, this is fixed. Temperature difference you have to fix, you have to give it, and time you have to calculate. If in some cases all are given, you should be able to calculate this permeability number. Okay, please do remember permeability is VH by PAT, and please do remember here these are all centimeters. Okay, not meters, centimeters, centimeter. Okay, fine. Okay, good. Next is permeability of water percentage. So this can be a graph also. This can be a question also. Okay, how? So what is water here? Water is the percentage of water that you're adding into the molding sand. You're adding into the molding sand. Okay. So what is that? If your permeability, okay, let me take this. Okay, this diagram is very important. So let's say you have taken sand, you have taken sand like this, and you added some little bit of water. Initially, what will happen? There will be some some kind of stickiness, isn't it? There will be some kind of stickiness initially. Because of that stickiness, air cannot pass properly. Air cannot pass properly. That's the reason why permeability is less when you are having less percentage of water. As the percentage of water is getting increased, into the molding sand, what is happening? Okay, this is what is happening. So these are 3 stages. Okay, initially these are your silica grains and these are your clay particles. Now if air wants to pass, it has to take so many tons, and here and there it has to pass. So this is having less time. So sorry, more time. Sorry, it will take more time. Because of that, permeability is very high here. Okay, and now if you increase a little bit of water, what will happen? Whatever this clay will be forming as a coating onto each of the silica particle. Okay, each of the silica particle. Now we have good space. Happily, air will pass easily. So time is less. It means permeability is more. That's the reason why permeability is increasing. And then after some time, if you further increase water, whatever gap is there, that is filled by the water. Now again, the air will not pass again, so the time will increase, permeability will decrease. That's the reason why permeability is decreasing. Okay, so that is the reason why if you are having small amount of water percentage, permeability is less, and then when it is increasing, the clay particles are getting attached to the silica grains. Because of that, more space is created. Happily, that air is being passed, time is less, permeability is more, increase in permeability here. And then after more increase of water, whatever the space is here, this space is filled with water. Again, the time is getting increased for air to pass, hence the permeability is less. Because of that, the permeability is coming down. Okay, is it clear, guys? Am I making myself clear here? guys? Okay, good. Next. Okay, good. Now, so what is, we can calculate this. What is the formula for permeability? See, 200 centimeter cube of air is allowed to pass through the standard cylindrical specimen for 1.5 minutes. So what is this? This is what? This is the volume of the air that is being passed. This is the time. This is the time. Okay, time that is being spawned. And manometer pressure difference. What is this? Oh, sorry. What is this? This is delta P or P. This is the pressure difference. What is the permeability for molding sand? What is the formula for permeability? Pn is equal to V into H by E, pressure difference, area of cross section into time. Into time. This is T. Okay. So volume. What is the volume? Pn is equal to volume is 2000 centimeters square into height. Standard is how much? 5.08 centimeters divided by pressure, that is 5 grams per centimeter square, into area, pi by 4 d, that is 0.5 whole square, into time 1.5. Then you will get the permeability number. Okay, then you will get the permeability number. This is the formula, VH by PAT, VH by PAT. Okay, so this is the solution. This is the solution for your answer, that is 66.87 centimeter per 4 per gram minute. Okay, fine. Hope you're understanding this. Next, another property for molding sand should be flowability. Okay, you're putting, this is pattern. Okay, this is pattern. You're putting pattern, and then you're putting sand and you're ramming it. You're ramming it. But if you're having some intricacies like this, the sand should go into that intricacy and settle, and then only know that kind of geometry is impinged onto the molding sand. If the geometrical aspects are not retained, then there is no point of sand, no? So the sand has to be flowing properly into the integrated shapes of the pattern, right? That is what is called flowability. It should be easily flowing. Next is strength. There are 3 different strengths: green strength, dry strength, hot strength. Green means sand containing with moisture. And then what is strength? Strength is nothing but, if you're trying to apply, if you're doing some compression strength or whatever it is, what is strength? When the moisture is there. Dry in the sense, you take this green sand sample, put it in oven for some time. If you're putting it in oven for some time, what will happen? All the moisture content is gone. Now when there is no moisture, there is no moisture, and that is known as dry sand. And still you're heating it. Now the sand is getting heated up. It is increasing its temperature, and that is called hot sand. So each one is having different strengths based on their, quantity of moisture into that. Okay? These are called green strength sand, dry sand, and hot sand. Okay? Hope you're understanding this. It means whatever I'm saying is that strength is important. Okay. Next, why sir? Why green sand, dry? Green, why? Because when you're pouring liquid metal, it is green status. Status is green in the sense moisture is there. When you're pouring liquid metal into the cavity, this sand is in green state, right? Green sand, right? Initially, green sand. Now, when you're pouring, it should not break it. It should not break off it out. It should be intact. So to make sure that it is not breaking, you have to have proper strength. Okay. After pouring, because of this heat, it will become dry. Because all the moisture will be lost because of the heat that you are pouring of liquid metal. Then also the strength should be there. After that, this is getting heated up and it is becoming hot. After that also, it should withstand the casting that you are pouring. Okay, because of that, 3 different strengths are important. Okay, so those are this green strength, dry strength, and hot strength. Okay, fine. Next is hardness. What is hardness? What is the definition of hardness? Hardness is having 2 definitions. One is wear resistance, another is indentation resistance. So one is wear or scratch resistance, and another is indentation resistance. Indentation resistance. Okay. So in our case, both should be there. It should not wear, the sand should not wear, and the sand should not have an indentation. Indentation is what? Because if you're having liquid metal like this, or you're having some pattern, you're putting some pattern, and then you're ramming it. When you're ramming it, uh, the what you say, the strength, the hardness should be more. If you're having good hardness only, when you are having removing the pattern, if you're having good hardness, what will happen? There won't be any indentation. There won't be any indentation that is being formed. There won't be any indentations. Or maybe when you are pouring, because of friction between molten metal and the sand wall, because here is where this is the line where there is a friction between molding sand and the liquid metal, and the sand should not flow away. It should not wear away. It should not scratch away. It should not get mixed into the molten metal. That's the reason why hardness is very important. Okay. And adhesive property. What is adhesive property? Bonding between two different materials. What is what are the two different materials? Because you are adding so many materials, so many things here, right? What are you adding? You are adding silica, clay, water, additives. So bonding between silica, clay, bonding between silica, water, bonding between silica additives, bonding between radio waters. All these things are called adhesive properties. And what is cohesive property? Cohesive property is bond formation between the same materials. These are small miscellaneous properties. And the last property is called collapsibility. Okay, this is very important. Okay, sir, I rammed it very hard. Very hard I have rammed it. Easily I have rammed it, sir. Amazing ramming, sir. Super, sir. Okay. Once you are pouring the liquid metal into this, now you have to break this. You have to break this node to get the casting out. If you are ramming very hard, who will remove that out? Very difficult to remove out. So you should not either ram very hard, or you should not ram very slow, very low, with low strength. It should be a medium strength, and that will come with the skill. That will come with the skill only. Initially, we don't know how much to ram. That will come with the skill. That is the reason why people do this apprenticeship. Apprenticeship, all these things they'll do in the foundry plant, so that they'll know what is the skill that they are trying to apply. Okay? Collapsibility. After all these things, it should not collapse. It should be collapsed easily. Okay. Okay. So now, what are the things that you are adding into the molding sand? I told you additives, sir. We are adding additives. So in this, we have clearly told we are adding additives, which will enhance the molding sand properties. So what are the additives? The additives are nothing but sawdust, wood flour, that will increase your collapsibility and permeability. You know, I told you already collapsibility, permeability also. So these two are improved by adding these two elements, sawdust or wood flour. Okay, and mold hardness will be improved if you're adding this molasses or dextrin or linseed oil. And your refractoriness, the ability to withstand heat, and good surface finish is also attained if you're adding graphite or if you're adding coal dust. So these are the elements that you're trying to add so that you're improving some properties. Molding sand properties. Okay, good. So okay, let's solve some questions again. Okay, what is the answer for where did we stop? I think we stopped at 11. What is the answer for 12th one? 12th one. Anyone? Answer for 12th one? Okay. What about others? Okay, somebody is saying C. Okay. B, C, B. What about others? Core prints are prepared in molds to support whom? We have discussed this. Guys, come on. Okay, B, C, C, B, B, C, C. Of course it is B. Of course it is B. We are supporting cores only, no? See, chaplets are supporting cores, but core prints are supporting cores. Okay, so please remember these core prints are supporting the cores. They're very important. You don't want your core to go up and down because of the buoyancy difference between the buoyancy force and the weight of the core. Core are the answer. Core prints are prepared in the mold to support cores. Answer is B. Okay. What about 13th one? What about 13th one? 13th one. Okay, everybody is on A. Tell me again. Just I'm the vocabulary from between class involved in the multiple. Okay, tell me. Okay, very good, very good, very good. 13th is of course A. Of course it is. So let's go from bottom. The capability to withstand the self weight and the pressure of the mold. So who is doing this? Who is doing this? Let's say the capability of self weight, all these things, molding sand will take care of it. Okay, and the capability of molding sand to withstand its own weight. No, no, right? The property to withstand expansion or contraction of the molding metal. No, it is only the capability of permitting the gases involved in the molding. That is what is your permeability, allowing the gases to vent out. Allowing the gases to vent out. Answer is A. Amazing. Okay, what about next one? What about next one? 14th one. 14th one. Cores are used to reuse, okay, produce integrated castings by placing this anti-environment force. Okay, it's easy, no? It's easy. Obviously, you're not enhancing permeability by using cores. You're not increasing the surface, you're not strengthening it. Obviously, to produce integrated castings by placing these items inside the mold cavity on core plates. That's it. Very good. What about next one? What about next one? 15th one. 15th one. Okay, I didn't say this, but anyway, try this. Yeah. Okay. A, you're saying A is a guess. Okay. Any other? So they're saying a small amount of carbonious material sprinkled on the inner surface of mold cavity is called. Okay. Any guess? Any guess, guys? Okay, I'll tell you what is backing sand. Don't worry. Somebody is saying dry sand. Okay. Any other guesses? Come on. Yes. Tell me. Any guess? I want some other guesses. Okay. Somebody is saying facing sand. Okay, fine. So answer is C. Okay, answer B. Okay. So I'll tell the other ones. Then I'll come to facing sand. Okay. First I'll tell about the backing sand. Backing sand is nothing but, so let's say you're ramming it. You have put some material and you've rammed it. Okay, you have rammed it. After ramming it, you have some places where some sand is not full. You have found that there needs to be some patchwork. So to fill the patching work, you use some backing sand. To fill the patches, you use the backing sand. Okay, it is used to back. Okay, back up. To use to fill the volume for the molding sand. You have to fill the volume. Okay, and what is facing sand? Facing sand is nothing but, okay, you're sprinkling it. So we have seen already here this thing, coal dust and this graphite. These are your facing sands. You will sprinkle once you are done with your molding cavity. Okay, let me say it here itself. So once you are done your molding cavity like this, and you just sprinkle these things here like this. You sprinkle it, and this is called your facing sand. Okay, and what are facing sand? These two are facing sands only, and this facing sand will increase the good surface finish properties. Okay, for better surface finish, sand which is used uh, after the pattern for better surface finish, And of course, this is made up of coal dust or graphite, which is increasing the good surface finish. Okay, so that is what is your facing sand. So answer for this question is what? Facing sand. Some carbonious materials. Carbonious, obviously, you can say coal dust and graphite are full of carbon contents, right? These two are filled onto the inner surface of mold cavity to increase the surface finish. Facing sand is used for increasing the surface finish. Please remember, facing sand is used or sprinkled onto the surface of the mold cavity so that you increase the surface finish. Okay, is it clear? Yes or no? Okay. Okay. So let's go. Good. Let's go to the next one. So that's the end of your what you say, the little bit of theory. From here we'll enjoy this portion because this is what where the casting comes into picture. All these things are important. Here, from here, the main casting is getting started. Main metal casting is getting started because all these things what we have discussed till now is are the primers, are the rudiments or the basics for metal casting. But here, from here, we are really designing it. We are really designing some sand casting. It's very important. Okay, so let's see what's happening here. One minute. Okay, so if you see here, already I told you. So there are two boxes. We have we have cope box and we have drag box. Okay, so and we have some core sand. Why we are using this core sand? We are using this core sand to make some hollow objects. Okay, and then here we have some pouring basin. We are pouring material into this, and then it is coming through sprue. What is the use of sprue? I'll tell you. And this is also known as down sprue. And then it is hitting the choke. And once it is hitting the choke, it is taking a sharp turn here onto the left hand side, and it is passing through runner. This is called runner, and then it is entering into the mold cavity. And this point, the entry point of molten metal into the mold cavity is known as ingate. Ingate, entering into the, this is gate kind of thing, gate into the mold cavity, and it is filling, and it is coming. These are called vent holes. These vent holes will allow your gas to escape. That is why we are providing this venting. This venting will provide permeability, allowing of gases to escape out. Okay, and then it is filling, and then it is coming up through the riser, and this riser is used for compensating liquid and solidification shrinkage. Okay, and this is how these things are. So what are the important gate? These are all called gating elements. Okay, these are called gating elements. What are that? Pouring basin. This is pouring basin. Sprue, and this is what is called choke, and then runner, then ingate, then riser. So we have to design them. You can't put whichever dimension that you want to have. There are some significances for this gating elements, and you have to design them. Okay, fine. So obviously, once you're pouring, and this is what is your casting will look like. And then what you do, this is your main object, and here you discard it, this also you discard it, and then this is what is your main casting object. Okay, and but still these are getting solidified. Anyways, you're discarding it. Anyways, you're pouring it also. You are not exactly pouring the same amount of material that is required for casting. You're pouring extra material because pouring cup, it will solidify here, it will solidify in runner, right, and it will solidify in riser also. But at the end you'll be using only this part. This part is very important for you. This part, that's it. Okay, you'll remove them. The extra gating elements will be removing on the casting. Okay, fine. Let's discuss this in detail. Okay, so this is the proper diagram for your with all the elements into the all the gating elements in the sand casting. This is sand casting. Okay, this is sand casting. Okay, so now what? So how the liquid metal is entering into the cavity? Let me say. Let me take some other. Okay, this pen. So what is happening? So this is called a ladle. This is called a ladle. It's kind of a bucket, but it can withstand huge temperatures. And you take this ladle, you go to the furnace, you fill the ladle with some material, liquid molten material, and then you bring it and then you pour into this casting. With it will try first enter into the pouring cup, then slowly it will fill the pouring cup like this, then it will enter into this, then it will come, it will enter into this thing called strainer. This is called strainer. So there are some impurities that strainer will catch it, and some good amount of material is coming and hit it. Because as you're coming down, the velocity is increasing, it will hit it, and as it is hitting, it should not disturb, it should not hit the molding sand. It should hit, if it is hitting the molding sand, then there is some kind of a damage here. You don't want that to happen. So what you do, you put some kind of a ceramic, this splash core, it is made up of ceramics. This is ceramic material, then it will hit, then again it will take a turn and it will go through this thing. This is called skim bob. Some lighter impurities will be caught here, some heavier impurities will be caught here, and then smooth stream will be going here, and this is called runner. This is called runner. Okay, this is called runner. And this is called ingate. Entry point of your liquid metal into the mold cavity, and then it will fill, and then it will go into the riser. This is called riser. Okay, so let's see the parts again. Pouring basin, then ceramic filter, then it is going to sprue, then it is hitting the splash core, taking a right turn, then skim bob is into the runner portion where it will collect lighter and heavier impurities, and then it is passing through the runner, and then through the ingate the liquid metal is falling into the molding cavity, and then it is rising through the riser, and this riser is reserved to, is used to avoid the shrinkage. Which shrinkage? Very important. It is avoiding liquid and solidification shrinkage. For avoiding solid shrinkage, what we are doing? What are we doing for the avoidance of solid shrinkage? Anyone? What are we doing for avoiding solid shrinkage? Guys? For avoiding solid shrinkage, what are we doing? Shrinkage allowance. So to whom you are giving it? Yes, pattern. Very important. Pattern is very important. Good. Fine. Now let's go. So all these things we can discuss. The main thing is that casting yield. Okay. Main thing here is casting yield. What is casting yield? Casting yield is nothing but volume of the casting divided by total volume that you are pouring. This is your pouring volume. So what is it? Okay, let me explain. Okay, here what is volume? This is the volume of casting. This is VC. Okay, and the total is total volume. Total poured is VC plus VG. The other parts is VG. So if VC plus VG is your casting yield, right? Yield in the sense like the profit that you're getting. If your gating elements are more and you're pouring more and more material, but after solidifying you're using only small amount of it. So you have to improve the casting yield, so that you have to have very minimal gating elements as less as possible, and you have to get good amount of casting for little amount of material that you're pouring. That is what is called casting yield. Okay, hope you're getting this point. Casting yield is nothing but volume of casting divided by the total amount of material that we are pouring, and that is also known as VC is volume of the cavity, VG is volume of the gating elements. Okay, fine. Next. So next is pouring basin. We are designing each and one of them. Okay, pouring basin. So why the pouring basin is like this? You have some small turn like this, then you are having like this, and you have some curvature, and then diameter is there. Why? You can't directly, you don't want to pour directly like this, because it will hit the molding sand. This is our molding sand. No, this is our molding sand. This is our molding sand. It should not hit it. So before you pour somewhere, then smoothly it is happily coming. As it is having a laminar flow, it won't disturb the molding sand. That is the reason why uh, what you say, the pouring basin is used. Obviously, your molding sand should not get eroded. It should not get eroded. So to avoid that erosion of molding sand, we are using this pouring basin. Okay. Next. Next is called sprue, and sprue is nothing but it is the part where your pouring basin is ending. Here, pouring basin is ending, and it is starting at this point, and then it is trying to allow the liquid metal enter into the mold cavity, and this is called top gating. Forget about this, but anyways, we are not using any runner and all these things. This is simple top gating system. Directly pouring basin, sprue, and it is getting into the mold cavity. And this sprue is not straight like this. It is not cylindrical like this. It is tapered. It is tapered. Why it is tapered? Why it is tapered? It should not be straight. It should be tapered like this. Top should have bigger diameter than the bottom. It means that D1 should be greater than D2. That's what I'm saying. Why we are not using this straight cylinder is to avoid this air aspiration effect. Okay, what is this, sir? What is this air aspiration effect? Air aspiration effect is nothing but, okay, I will tell you. So this is what, let's say this is 0.1. Let's say this is 0.2 and this is your 0.3. Okay, 0.1 is open to the atmosphere. Am I right? It is open to the atmosphere. Okay, and 0.3 is also open to atmosphere. Okay, and 2 is not open to atmosphere. It is somewhere in between the liquid metal stream. Okay, now if you are applying Bernoulli laws between 1 and 3, 2 and 3, something like that. Bernoulli's, what is Bernoulli's? Bernoulli's law, right? Bernoulli's right? What is that? Anyone who can say what is Bernoulli's law or Bernoulli's principle or Bernoulli's equation? Anyone? In fluid mechanics, have you heard of Bernoulli's principle? When we were kid also, we have heard of Bernoulli's principle, right? Yes. So what was that? Your pressure energy plus potential energy plus what? Kinetic energy is equal to constant. That is what is your Bernoulli's principle, right? Right. So if you're applying this Bernoulli's principle between these points, what will happen is that if your sprue is straight, again I'm saying if your sprue is straight cylinder, then at this point too, there is a negative pressure that is created. Negative pressure is created when, if your sprue is straight cylinder. Okay, if your sprue is straight cylinder, then if you're applying some Bernoulli's principle and continuity, A1 V1 is equal to A2 V2, all these things, we are not doing the derivations, but anyways, the derivations are here in this thing. You can see if you want, but I'm not discussing here. Okay, we have a very limited amount of time. So here, some negative pressure is created, and if negative pressure is created somewhere in between liquid stream, what will happen? What will happen? What will happen? What will happen? When negative pressure is created, obviously air, let's say air is 1 atmosphere outside and some negative pressure is created. Obviously this air will be sucked here. Am I right or wrong? That air will be there, which will be there in atmosphere, will be getting sucked inside, because obviously anytime the the fluid or something will be passing from high pressure to low pressure, right? So high pressure is here and low pressure is here at this point. Low pressure is there at this point, and air will be sucked, and that air or that ambient air is sucked inside, and then it will come inside and it will mix here inside this. Because of that, some air bubbles will be formed. That is not good. To avoid this air, this is called air aspiration effect. This is called air aspiration effect. At the inlet of sprue, negative pressure is created, and that that creation of negative pressure is creating some air to get sucked inside, A2 gets sucked inside, and because of that some defects are being formed, and that air is, hello, yeah, that is called, this creation of negative pressure and air is getting sucked inside is known as air aspiration. Now what we have to do is that we have to avoid it. I don't want to create negative pressure, first I have to avoid it. So to avoid that, I do some calculations and then I say that yes, I should have this kind of structure, this kind of geometry of my sprue, so that I can I can avoid air aspiration. Okay. Now, if you're having little bit of bigger diameter and little bit of smaller diameter here, then what will happen? There will not be any negative pressure. Maximum it will reach to the atmospheric pressure, which is almost same as atmospheric pressure outside. So then there won't be any, as there is no pressure difference, obviously there won't be any air suction. Okay. So please remember, you have to have a tapered section, cross section, so that you can avoid air aspiration effect. Isn't it clear? Yes or no? Am I right? Am I making myself clear, sir? Everyone is getting what I'm saying? Very good, very good, very good. Next. So that is what I told. I told you, getting elements, air aspiration effect, gases may enter into the mold cavity through molten metal if pressure anywhere in the liquid becomes negative. That's what I told. A, pressure anywhere in the liquid medium should not become negative. Then what we are using this, all these things I'm skipping it. This is what is Bernoulli, pressure energy plus kinetic energy plus potential energy is constant. This is your formula. Then I'm taking some points. Then second term, okay. Here this is height of the cup. Height of the cup means height of the pouring cup. This is height of the pouring cup, and this is height of the sprue, and this is total height. So HC is equal to, HT is equal to HC plus HS. That is height of the pouring cup plus height of the sprue is the total height. Okay, and this is open to atmosphere. This is also open to atmosphere. This is your mold cavity, and this is your base of reference. From this is where you are taking your reference from. Okay, so you're applying more or less equation between point, uh, 1 and sorry 1 and 3. Then you're getting some, you're using some continuity equations. You can follow this derivation. When I'm sharing the slides, you can follow the derivation. If you are having any problem to understand the derivation, I hope you will understand it because it is very clear. If you're not getting it, don't worry, I'm here to explain you. But anyways, I'm skipping this because it's not important now to discuss because we don't have much time. Okay, and then again I'm applying Bernoulli's between 2 and 3. Okay, and then I did some calculations here and there, and then I found out that this thing. That is what is that? A2 should be more than A3. That is what I found out. A2 should be more than A3, and A2 is more and A3 is less. And this is actually, it should be like this. It should be a paraboloid. It should be paraboloid because this is the equation you're getting. A3 square by A2 square is equal to HC by HT. It is Y square is equal to H. It should be parabolic. Actually, it should be like this. Even though the diameter is more here and less here, really it should not join as a straight line. It should be joined like this, like a parabolic curve. But due to some manufacturing constraints, because this is a small thing and you don't want to make it parabolic, manufacturing is little difficult if you're making it in a mass production. So directly straight, tapered. You're putting it a tapered. So this kind of tapered sprue is used to avoid air aspiration effect. What is air aspiration effect? Air aspiration effect is nothing but somewhere in the middle of liquid stream, you don't want to have any negative pressure created. If negative pressure is created, some air particles may be sucked inside because of the pressure differences. That air particles may be mingled or mixed into the molten stream and getting into the mold cavity, and that will be forming some defective casting. I don't want that to happen. Because of that, I am designing this kind of sprue. Clear? Yes or no? Guys? Okay, good. Okay. Next. So this is what they've asked in GATE. I'm not going to solve it. It's very easy. What they've given, they have given this cross section. Some area is in here. They are saying that what is they trying to, they've given some question. Okay, they are saying that to avoiding air aspiration effect, what should be the area at this bottom? That's what they're asking. Okay, so the solution is this. So what I did, I took some, A2 is given, you have to find A3. So then I did some Q is equal to A2 into V2. You can apply continuity theorem between here and here, right? A2 into V2, area of cross section here into velocity at here is equal to area of cross section here into velocity at this point. And then I found out what to say, the V2. Then for calculating V3, I used Bernoulli's theorem between 2 and 3. I found out V3. Once you are finding V3, you have A2 into V2 or you have Q, so you can find out this A3. That's how I found out A3. The solution is given. Go through this thing. This kind of complicated things he will not be asking in HL examination, but yet he'll be asking some very simple questions. Okay. Please remember, he might be asking this question as well, right? If okay, 1 minute. Okay, so he might be asking, what is the shape of this sprue? Or diameter of top of this sprue should be greater than the diameter at the end of the sprue, or it should be equal, or it should be less than. None of the above. Like that, he'll be asking some simple conceptual questions. Okay, fine. Now, runner. Okay, before going into the runner, let's solve some questions. Let's solve some sprue questions. Okay, so where did we stop? We stopped at 15. Okay. 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 The velocity of the molten metal of the stream. Okay, can anyone try this? Can anyone try this? Give a try at least. I didn't discuss this, but if you have some idea, can try. But anyways, I'll solve the question. But please try this if anyone can try. It will be much appreciated if somebody can tell the answer. Okay. 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 Yes, you are right. You are right. All of them are right. They are saying the velocity of molten metal stream at the base of sprue of height h is. It's easy. It's a simple, easy thing. I'll solve here. I'll solve it here. So here, what is that? They are saying height h, and they're asking what is the velocity at this point. What is the velocity of this point? Okay. So what you can do? You can apply some kind of Bernoulli's theorem. Bernoulli's theorem. Okay. So let's assume you have. Okay, I'll show it here. Answer is here itself. I'm not showing it. Where is that? Yeah. Yeah. So this is the answer. The velocity of the sprue at the bottom of sprue is under root 2gh. How we got it? How we got it? We got it by applying Bernoulli's between 1 and 3. 1 and 3 you apply Bernoulli equation. So what is the Bernoulli equation? Bernoulli equation is P by rho g plus V square by 2g plus h is equal to constant. So what is Bernoulli's equation at 1 and 3? 1 and 3 is P1 by rho g plus V1 square by 2g plus h1 is equal to P2 by rho g plus V2 square by 2g plus h2, right? So we have taken this as our reference. So h not 3 3 3 1 and 3 1 and 3. We are applying between 1 and 3. Okay. So as we are taking base at 3, height is 0. This height is 0, right? And this height between these two is ht, right? So h1 is ht here. P1 and P3 are same. P1 and P3 are same. Why? Both are atmospheric. This is atmospheric. This is atmospheric. P1 and P3 are same. And velocity at V1, this velocity at V1, we are assuming it to be almost zero. Why? Because it is maintaining constant head. This level is not coming down. That level is maintaining there only. Because if you are increasing the level, it will overflow. If you are decreasing the level, it means the liquid metal is over. But we are maintaining the constant level. So V1 is almost zero. So then V1 is also zero. So what is left? HT is equal to V3 square by 2G. Right? So V3 is what? V3 is what? Under root 2G HT. So what is V3? V3 is the velocity at the bottom of screw. Velocity at the bottom of screw. It's under root 2G HT. Is it clear? So that is the answer. That is the reason why the answer in this question is 2GHT, but it is 2GH, under root 2GH. Okay. Yes. Next. What is 17th one? What is the answer of 17th one? 17th one. Come on, read the question. Please read the question. I got different. Why it is B? Why it is A? Praveen, Naveen, please read the question. Don't be in hurry. Please read the question. Yes, yes. It is air aspiration effect. It's easy. Air aspiration effect, right? Pressure anywhere in the molten solution should not fall below the atmospheric pressure, and this is essentially to avoid. You don't want to have any negative pressure, and that is we want to avoid this thing that is called air aspiration effect. Okay, come on, next one. What is the answer of next one? 18th one. 18th one. What is the answer? 18th one. 18th one. Yes, it is parabolic. We have seen it clearly. Yeah, yes or no? Yeah, we have seen it. See, it was parabolic. Ideally, it should be parabolic, but for making manufacturing, there's a manufacturing. Now it is not. This was previously. This was like long back, from centuries. If they are doing this, for because of this manufacturing constraints, they are using tapered. Now we can use even you can try to make parabolic also for more accuracy. So it's parabolic. The the screw should be like this. Keep remember thumb rule. Top diameter should be more than the bottom diameter or top or cross section. It's not only diameter, it can be a square one also. Top cross section should be more than the bottom cross section, and the both top cross section and bottom cross section should be joined by a parabolic curves, parabolic surface. Okay, fine, good, good. What about 19th one? 19th one, come on. 19th one. Come on, read the question. Read the question properly. Read the options properly. Anyone? Okay, 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 fine. So she is asking, a sprue is a small piece of perforated tin sheet placed in the pouring basin at the top of the down sprue. There is no meaning of this. Leave it. At the opening through which molten metal enters into the molten cavity. So this is a possibility. Okay, fine. Let's see. The channel through which molten metal is brought into pouring basin plane. Okay, this can also be an option. Why? See, this top sentence, that top statement says that it is entering into the molten cavity. It might be. For top getting, it is true. The channel through which molten metal is brought into, of course, from pouring basin only, no, that channel is there. For pouring basin only, the channel is connected. This also can be an answer. The shortest pouring path to avoid the pouring, no, this is not the answer. Okay. So here there is a discrepancy according to me. The answer can be B or C, because in this Bth option, what they're saying that molten metal is entering. So for top gating, it's true. For top gating, it's true. If you are seeing bottom gating, I'll show you the bottom gating. Where is the bottom gating? Yeah, in the bottom gating, your end of sprue is not entering into the mold cavity. Your end of sprue is connected to runner, and then runner, at the end of runner only, that and it is entering into the mold cavity. So if you're considering it to be a bottom gate, then option B is not giving the right answer. Option B is not giving the right answer. So option C, what is option C? The channel through which molten metal is brought into the pouring basin. Okay, so it is from pouring basin, there is a channel that is connected to the pouring basin through which your molten metal is entering. So option C is not having any ambiguity. It is perfectly right. Option B also is right when it is top gating. If the question is specifically mentioned that it is top gating, then B is answer. But for a bottom gating, this is not true. B is not true for a bottom gating. Okay. So the channel through which the molten metal is entering into the position, this is the right answer according to the question. See, answer can be so many things, but depending on the question, answer will be changing. Okay. So according to me, the answer is C. Are you getting my point, guys? Any problem? If anyone is disagreeing with me, let me know. Anyone? Are you getting my point? Clear? Yes or no? Okay. Okay. What about next one? What about next one? What next one? Come on, 20th one. Okay, Bipin is C. What about others? Okay. Okay. Praveen is C. Naveen is C. Bipin is C. Prabhakar is A. Okay. Guna A. Mohammed C. Ashrad is C. Okay. See, strainer, it's not sure. No, it is catching some impurities. That's okay. But I didn't say anything about whether they are lighter or heavier. But I did say that in the skim bomb, skim bomb is that clearly I said in skim bomb you have some lighter impurities that are caught here in the top one. So answer is skim bomb. Okay, answer is skim bomb. Is it okay? Answer is C. Yes. Fine. Fine. So let's stop the questions again. Let's go back. Let's go back to the uh, slides here. Come on, what is happening here? Yeah. So let's discuss for some five more minutes, and then we'll close up for the session. Then we'll proceed in the next class. And next class will be more exciting because we'll be entering into solidification, and good amount of questions are on the list. Okay. Fine. So then, okay, we designed pouring basin. Okay, we have designed riser, and riser we have designed such a way that it is avoiding the air aspiration effect. Fine. Now, after taking a sharp turn, it is hitting some ceramic core, and then it is taking right turn. Then it is entering into runner. Runner can be of two geometries. Okay, the first geometry is this. That is a cylindrical runner or a trapezoidal runner. Okay, cylindrical runner or a trapezoidal runner. What is that? Cylindrical runner is used to minimize the heat transfer. How? Why is that? Why cylindrical runner is minimizing heat transfer? Because it is having less area of cross section or less area of surface area, less surface area, like that. less surface area. Because of that, the heat transfer is not very high. Heat is maintained. Why to maintain heat? Because it is coming from pouring basin, all these things, it is entering into runner. If your heat is not, if you're losing heat, then by the time it is flowing here, it will get solidified. You don't want that to happen. You want to get your heat retained. Okay, that is one. Or sometimes, in some cases, in some very light materials, light density materials, what happens? There is a chance of very light, very fastly they'll flow, and some kind of turbulence that is created. To avoid that turbulence, you are using this trapezoidal runner. Okay, so two chances. One, you are using cylindrical riser to minimize the heat transfer. Two, you are using trapezoidal runner to minimize the turbulences. Because of that, erratic mixing of fluids. What happens? It might create the molding and eroded. You don't want that to happen. Okay, right. Next is what? In-gate. So we are done with sprue, pouring basin, sprue, runner. Then in-gate. In-gate is this. So in this top gating system, sorry, 1 minute. In this top gating system, this is in-gate. So please remember, in-gate. In bottom gating system, this is runner, and this is in-gate. So in this both cases, this is your cavity, and this is your cavity. Okay. In both the cases, the entry point of liquid metal into cavity. So that is what is called in-gate. So in that in-gate is having top gating system, that is what we have seen here. Bottom gating system, that we have seen here. It means what? You are pouring it from top, like a bucket. You're having a bucket, you're putting under tap, and this is kind of a tap, and this is your bucket. That's okay. But sometimes it will be bottom. Like instead of connecting the entry at the top, you're connecting the entry in the bottom. This is the bottom, no? This is the cavity. This is the bottom gating. Okay. And then parting line gating. What is parting line gating? Nothing but this is your mold cavity, and this is your parting line. This is first half, second half. You're connecting your gate at the parting gate. So when you're adding to parting gate, this is top gating for the bottom portion, bottom gating for the top portion. Okay. That is what is your parting line gating. Step gating, you have so many steps. Okay, like this. You have so many step 1, step 2, step. I'll show you the step gating thing. Okay, don't worry. So let me discuss top, bottom, parting, and step. Okay. So this is what is for top gating. In gate. 1, 2, 3. Height of the pouring cup, height of the sprue, that is HT, molding height, area of the cross section of mold. Okay. And this is your bottom, your top, your in gate is at the top of your mold cavity. Your in gate is at the top of your mold cavity. Okay. And then please remember, already this question has been, we have discussed this question, that is the velocity at the entry, the velocity at which the molten metal is entering into the molding cavity is given by this formula, that is under root 2gHT, and we have seen that is this has been derived by using this, applying the Bernoulli's theorem between 1 and 3. We have already seen that in the previous slides. Okay, so please remember, very important formula. This formula is very important. Okay, next. So what are the importances of top gating? What is the importance? Liquid metal enters directly from bottom of the sprue at the atmospheric pressure. So directly bottom of the sprue entering into the cavity at atmospheric conditions, because this is atmosphere 1.2 also atmospheric conditions. Next, velocity of liquid metal in the cavity is very high. Obviously, because it is flowing from top. No, velocity is very high from top, right? There is a chance of turbulence and splashing of liquid metal. Okay, because have you ever seen if you are filling the liquid? So I'll tell you two cases. Let's say this is bucket and this is your tap. This is your tap. Okay, and in another case, this is your tap. This is your tap like this, and I've taken pipe. I've taken a pipe and I'm connecting it at the bottom like this. And now water is filling like this. Water is filling like this. In these two cases, case 1 and case 2, who will have more turbulence? Who will have so many mixing that can happen? Which will have more turbulence? 1 and 2? Obviously 1. Obviously 1. Because it is falling here, so much of turbulence is there. But here it is coming and slowly it is going up. There is no point of turbulence. Water is happily filling up. If you see water, you don't even know that water is being pumped from. Happily the layer is getting increased. Slowly you'll see that. Okay. So obviously the turbulence is very high in the top gating. It is not used for casting of non-ferrous. It is used for ferrous actually. Why? If you're using non-ferrous is very light material. Already it is having turbulence. Because of light material, more turbulence is created. That's the reason why you can't use this gating system for light materials. You can use the system only for ferrous. Or I can't say only for ferrous. I can say that you can't use it for light materials. That is very important. We cannot use this gating system for light density materials because of turbulence. Okay, very important. Next. So what are the lightweight materials? Aluminium, copper, magnesium. So aluminium, copper, magnesium, we should not use top gating if you're trying to casting with aluminium, copper, magnesium, because their density is less. And there is a favorable temperature gradient of liquid. Favorable in the sense like the what you say, the gradients. This will cool first, then this will cool. Slowly the cooling gradient is from bottom to top. Happy, very nice gradient that is being formed. But in bottom gating, please remember. Okay, this is what. Okay, now in top gating itself, forget about all these things. If you are trying to fill from top gating, and if your height of the mold is this, and area of cross section of the mold is this, and volume is how much? Volume of mold is equal to HM into AM, height into area of cross section. So what is the time of filling this volume using top gating? TFT is time of filling for top gating. How much time it will take to fill this thing? That formula is given by this. Volume of mold, that is AM into HM divided by area of the ingate, area of cross section of ingate into velocity at that ingate. Again I repeat. The formula is this. Time of filling of top gating is equal to volume of the mold divided by area at ingate. It means that the cross section at this point, is AG. Okay, and VG, velocity. The velocity. What was the velocity? What is the formula of this velocity? We have done this. That is under root 2G HT, total height. What is HT? HT is nothing but HC plus HS. Okay, so TFT, if you write, it is AM into HM by area of the ingate into under root 2G HT. This is the formula. You have to remember this formula. Or you can remember this formula, then you can easily remember. Okay, volume of the mold divided by area of the gate into velocity at the gate entry. Okay, So that is what is the time of filling for top gating system. Time of filling for the top gating system. Is it clear, guys? Am I making myself clear here? Okay, fine. So let's stop here, and tomorrow we'll discuss about water gating, and slowly we'll discuss about solidification. Then we'll design riser. Then we'll discuss on something about miscellaneous castings, and as usual, we'll be solving some problems as we complete the topic. Okay. Hope again the session is informative, and hope you have learned something which you didn't know, and we'll continue to do this thing as we proceed with the lectures. Thank you. Any doubt you can ask me. I'm here, and if you're done, you can take 1 hour gap so that you can attend another class after 1 hour. Okay. Thank you. Thank you. Thank you. Yeah. Thank you. Sure. Sure. And also, I have shared the questions as somebody has requested. If you have already prepared for gate, if you know some concepts, try to attempt them before itself. Don't waste time. Have you seen that HTML, that file is opening, right? You can see the questions, right? Yeah. Okay. Okay. Fine. Yeah. Good. Good. All the best. All the best. Happy learning. If you are very sincere enough, I suggest you solve previous year engineering questions also, objective type. It will be very helpful. Very helpful. Okay, fine. Yeah, any doubts you can ask me. I'm here. That's it. Or else you can leave. Thank you. Yeah, thank you.